When people think of lasers today, they're most likely to think about a laser pointer or a barcode scanner at the grocery store, maybe the tiny laser in the printer that we use in order to put toner down on a piece of paper. But the properties of laser light allow us to do so many amazing things with them. Did you ever wonder what we can do with lasers? What is it that makes laser light special? Laser light is really just well-behaved and well-ordered light. I can demonstrate using a flashlight and a laser pointer. If I take my flashlight and I shine it on the paper, I get a nice tight dot of white light. But as I move the flashlight away and away, that dot becomes more and more diffuse and the light is more and more spread out. In contrast, if I take a laser pointer and I put my spot on the paper, I get a nice tight spot. And as I move the laser away, I still have a nice tight spot. And as I move away and away and away, the spot doesn't change. Our laser light is staying together, it's staying well behaved. So as we think about the difference between our laser light, where each and every photon is exactly the same, going in the same direction, and our general white light, where each and every photon is different and they're going all over in whatever direction they'd like to, we can use an analogy of folks running. If you imagine a group of soldiers going out for a jog together in formation, they're all lined up shoulder to shoulder, and one of them is calling out the cadence left, right, as they step, step, step. And if we could freeze them in time, we could pull out a tape measure and we could measure how far it is from the one on the left to the one on the right, and how far it is from the one in the front to the one in the back. And then we can let them go off on a long run, 10 or more miles, and then just as they're about to finish, we can freeze them again, pull out our tape measure, and those measurements would be exactly the same. That packet of soldiers is like a pulse of laser light. In contrast, if we took a group of casual runners that all happened to start at the same time, at the beginning of the run, they'd all kind of be in the same place. But after they each run for a little while and they head off in different directions, they're all going to spread out and they won't be together like that group of soldiers is. The fact that all of the photons in the laser light are exactly the same and they're doing exactly the same thing, going in exactly the same direction with exactly the same phase, is what makes laser light so useful. We can use it to very articulately move energy or information from one place to another, and it's very easy for us to control the way that we're doing that. Another way that we can capitalize on the properties of laser light is with large-scale experiments like the ones that we do at the University of Rochester's Laboratory for Laser Energetics. At the LLE, we're fortunate enough to have 2 giant laser machines, and either one of these laser machines can put about 30,000 joules of laser light on the target in the target chamber on any given shot. One of the amazing techniques that has been developed at the U of R's Laboratory for Laser Energetics is a way for us to not only focus the light in those 2 dimensions that the lens takes care of, but also to shorten up its duration, to compress that pulse from being a nanosecond scale laser pulse where it's convenient for us to amplify it, down to a picosecond laser pulse, or one that instead of being 1/3 of a meter long is paper thin. Now this work, called chirped pulse amplification, was so impactful that it was awarded the Nobel Prize in Physics in 2018. Having these huge lasers that we can very accurately control has been an enabling technology for the field of laboratory astrophysics. I think it's astounding to just say those words, laboratory astrophysics, doing astrophysics in the laboratory. For thousands of years, humans have been doing observational and theoretical astrophysics. We've looked up at the sky and thought about what we saw. Later on, we developed telescopes and other instruments that we could use to better look up at the sky. But still, the things that we were studying were out of our reach. And then we were applying theory in order to try and understand what was going on. Today, if you want to study an astrophysical event, like say a supernova remnant, for example, we can create those conditions in the target chamber using our lasers, and then we can bring to bear the diagnostics that are right here in the laboratory in order to accurately measure it. It'll only exist for a short period of time and it'll only be very small, but it will be an accurate representation of those events. Laser technology continues to move forward. Every day, scientists are discovering new ways to make laser light, new ways to control it, and new applications that we can use to make the world ever better.